Climate change is posing unprecedented challenges to our generation. While clean energy is one step towards a durable solution, leading the transition to renewable sources in heavy industry requires wide availability of high-performing materials, able to withstand extremely harsh production conditions. This situation is getting exponential attention at European level, giving rise to research initiatives such as the SEMWAVE project.
The SEMWAVE project was born to answer for Europe's demand of new materials able to survive in the always more aggressive and fluctuating environments expected from the increasing usage of renewable energy sources in energy-intensive sectors. So materials able to withstand such demanding conditions and having at the same time high energy-efficient performances do already exist, but due to their high production cost, they are not yet used in these sectors. And these materials are the ceramic matrix composites.
Ceramic matrix composites are not entirely new materials. They've been around for about 30 years now, but they are really developing fast these days, and there's a tremendous interest globally in using them. And the question is why? They are materials which are very high temperature capabilities, in general higher temperature than most metals. They offer very good toughnesses compared to the straightforward uncomposite, the advanced ceramic material. So these are being looked at by a very wide range of industry, from the military right the way through aerospace and into manufacturing industry. And this is a global phenomenon.
While the high manufacturing costs have kept CMCs off limits to many industries, the technologies employed in SEMWAVE research, together with the integration of renewable energies, aim to drive down production costs.
In the framework of the SEMWAVE project, we would like to propose the application of an innovative microwave-assisted chemical vapor infiltration technology to manufacture economic ceramic matrix composites, reducing strongly the processing time involved to manufacture them, while at the same time making their usage more sustainable. Specifically, the use case of the SEMWAVE project will be the development of a CNC-based tube in order to be tested in the relevant environments of interest for steelmaking applications inside radiant tubes. In fact, inside this application, since all these processes will have to be adapted to have an increasing usage of renewable sources as hydrogen or biogas mixtures, will require to adapt and to have a modernization of their processes in order to reduce their related energy consumption and CO2 emissions. And so we would like to propose the replacement of the currently employed Inconel and stainless steel material with those CMC manufactured through this cleaner and innovative approach. Different challenges will be addressed throughout the SEMWAVE project, which will involve different fields, from the CMC material field up to microwave-assisted technologies for industrial applications, since we are speaking of high-temperature applications. As far as concern, for example, microwave application, one of the major challenges has always been the control and tailoring of a well-defined heating pattern of on-performs. And this challenge has always been slowed down due to the usage of old microwave magnetron sources. Instead, throughout the SEMWAVE project, we would like to propose the replacement of magnetrons with the latest solid-state sources that, thanks to the fast and precise control of the frequency, will allow a finer tuning of the operating parameters to achieve a higher quality product.
A first crucial step to deal with is the development of CMC preforms.
The preform architecture depends on the winding angle using the winding machine for both for the oxide and non-oxide preforms. And we have here in the same way two aspects which we have to care about. The first aspect is that we get enough open porosity in non-oxide and oxide preforms for the later microwave-assisted CVI densifications of the matrix. And on the other hand, we also have to look on the mechanics of the system. When we only focus on the porosity, then may the tube have no mechanical strength in the later high-temperature application.
To achieve weak matrix interface, all the ceramic fibers were previously coated.
Normally, the coating is necessary to protect the fiber against corrosive attack during the later application at high temperature or during the process of manufacturing. And the other thing is that the coating is necessary to weaken the bonding to the matrix, so that you really have a weakened interface between the fiber and the matrix, and therefore the coating is essential. We use a multi-layer system which we apply by using wet chemical infiltration technique from a roll to roll point of view. So there we can coat the fibers in a continuous way. So this is very important for the low-cost aspect in this project. This would be the first time in the world that we have an aluminum oxide, fiber-reinforced aluminum oxide, where the matrix is absolutely dense and not very porous.
Then, the CMC tubes are delivered to University of Pisa and University of Birmingham to apply the microwave-assisted CVI process for further densifications.
We are trying to take materials which don't absorb microwave energy and therefore don't get hot, and heat them with microwaves, and heat them inside out with microwaves. So our goal here is to try and develop materials which operate on a different mechanism, known as weak interface, where the interface between the fibers and the matrix is, as its name implies, weak. This gives you a high toughness, but also much greater strength. The equipment we have here at the University of Birmingham is reasonably unique in that there are only two such systems that I'm aware of. The first is at the University of Pisa in Italy, and the second is here at Birmingham. Both were put together at around about the same time. Like the one at Pisa, ours originated in working on silicon carbide-based composites. But for this program, we've had it adapted, so we can now work on oxide-based composites.
The required adaptation of the system included the application of a microwave-absorbing carbon coating, which allows the fiber preforms to be heated to around 600 degrees Celsius.
The materials on which we work are produced by other partners, as Fraunhofer and ATL, which is a company. Then we use, as I said, the thermal properties of these materials, which are characterized by other partners as CNRS and Enea. Then we make the real-life infiltration test by using the reactors owned by University of Pisa and the University of Birmingham. And then we have also a good and strong relationship with a partner providing the electromagnetic sources, which is Frick-Muller, and also with a partner, IRIS, that is helping us to build automatic procedure of the control of the reactor. The approach we followed to obtain this monitoring of the dielectric properties during the infiltration process was based on the design of the reactor as a multi-frequency system. So the reactor becomes a kind of electromagnetic system working at a high frequency, which is the frequency of the heating process, and to a low frequency, which is the frequency of the monitoring system. In the dielectric characterization, we basically determine the way in which the samples of interest interact with the electromagnetic fields. In particular, we try to determine how this material distort the electric fields and how much energy these materials absorb from the electromagnetic wave. This information is crucial because it gives the possibility to compare the efficiency of the microwave-assisted chemical processing with other more standard techniques. The optimization of the microwave heating process from the electromagnetic thermal point of view is based on the numerical modeling, or the mathematical modeling of the reactor loaded by the sample. What we do is to calculate in the system the electromagnetic field distribution inside the reactor and inside the sample, and also the temperature distribution inside the sample for different microwave frequencies and power. Then we take a look to the results with the idea of finding what we call the optimal working condition, so the microwave frequency and microwave powers which guarantee the most homogeneous heating of the sample. Once we found different possible conditions of good microwave heating, we combine different frequencies and different power in order to have the best possible temperature uniformity inside the sample.
This modeling is multiphysics modeling, in the fact that we have to combine many physical and chemical phenomena together. The center of the process is heat transfer. So we absolutely need to have a good idea of what are the thermal gradients in the material, what are the temperatures everywhere. For that, it is necessary to go in the electromagnetic modeling, because the heating is provided by the microwaves. And on the other hand, these thermal gradients are very important in controlling chemical reaction. Therefore, the rest of the modeling addresses chemical reaction and also the transport of the chemical species. So this is why, if you combine everything together, electromagnetism, thermal transfer, mass transfer, chemical reaction, and the material's structural evolution, then we have something that's clearly multiphysics.
Advanced modeling was also applied for designing specific ceramic inlays to be inserted inside of the heater's tubes.
These ceramic inlays are designed to maximize heat transfer from the burnt gases to the walls of the tube, so that the walls of the tube may radiate more efficiently on steel. And the design was based on computation, first on CAD, computer-aided design, properly designing the structure. And the second part was to achieve thermal computation, thermal transfer computation, in order to assess what would be the heat transfer exactly using those structures inside the tube, and try to quantify the amount of efficiency that these inlays would bring to the whole radiant tube.
Finally, the manufacturing of net-shaped ceramic components requires large and complex parts which can be built by joining.
Many materials have been tested for the joining in the SEMWAY project. In the joining of oxide-based CMC, we managed to obtain two successful glass ceramic for the joining of this composite, and we also managed to publish a scientific paper in this regard. And then also for the joining of non-oxide-based CMC, we are currently working on glass ceramic, then we think and we believe it's successful for the joining. We are also using another material, for example, brazing alloys, for the joining of oxide and non-oxide CMC. In this case, we need to have different brazing alloys for the two different properties of the composites.
As a final step, the CMC tubes will be tested at industrial operating conditions on a steelmaking testing plant of ArcelorMittal in Spain, using hydrogen as fuel.
Explicar de una manera sencilla en qué consisten estas pruebas sería decir que nosotros tenemos un nuevo material que queremos comprobar cómo funcionaría en condiciones reales. Entonces lo que tenemos es en un tubo real, hemos quitado una parte de ese tubo y hemos diseñado un portamuestras para poder meter la muestra de este material, que es más pequeña, no era posible construir un tubo completamente con este nuevo material. Lo vamos a poner dentro de la cámara de combustión, que es en la que normalmente hacemos las pruebas, y vamos a añadir un quemador que va a quemar el gas, en este caso hidrógeno, para que el tubo caliente hasta una temperatura de trabajo que podría ser unos 900 grados o 1000, dependiendo de las condiciones, y vamos a hacer un seguimiento del comportamiento de este material por medio de una sensórica que se ha definido para este proyecto.
Esas cámaras van a estar encendidas de manera continua, entonces van a poder ver desde que se arranca la prueba todo el calentamiento que sufre ese material, cómo se va comportando con el tiempo y qué degradación puede tener a lo largo del tiempo. Entonces, esas cámaras van a estar guardando todas las imágenes en un servidor específico y esas imágenes van a ser después evaluadas para ver cómo se ha comportado el material.
But the scale adaptation was one of the major hurdles to overcome.
Estás pasando al final prácticamente de lo que es un laboratorio, una escala de laboratorio, te estás saltando la planta piloto y estás intentando hacerlo sobre un demostrador de una planta industrial con las condiciones industriales. Entonces, al final son prácticamente dos cambios de escala. Entonces, lo que haces en cada uno de los cambios de escala es modificar mucho los parámetros de control. Entonces, al final, tanto para nosotros como para el resto de partners, esa confluencia entre lo pequeño y lo industrial, yo creo que ha sido el mayor reto para todos.
The SEMWAVE project is in its last stages, and in the following months, further challenges are still ahead regarding the validation process of the CMC tube. The expected outcome is a possible exploitation of the concept in the next generation radiant tubes.
We are always looking for the transfer to industrial partners. That's one of the main goals, not only in this project, but I feel, the results are promising, and there are other fields of application besides steel industry where we can use such results and can address partners if they are interested in testing a prototype based on this technology.
Perhaps within the next 5 to 10 years, the materials we're making will start to find their way into industrial production. It won't happen overnight, these things never do.
Ceramic matrix composites are creating opportunities for heavy industries to rethink the way they work and for them to switch to clean energy. This not only enhances efficiency, but also marks a crucial step towards minimizing carbon footprints. With initiatives like the SEMWAVE project, we're witnessing a pivotal shift towards embracing new manufacturing technologies at an industrial scale, fostering a future where sustainability and innovation go hand in hand.